Okay, so the last in this series, and now we're finally going to get around to talking about what microevolution actually is. So let's do that. So the definition of microevolution, this really should say microevolution. Sorry, that's messy. Microevolution is the change in allele frequencies of a population over time. So alleles for now, I said we'd come back to this, right? For now, we're just going to say that alleles are genes, okay? Actually, that's not entirely true, okay? But for now, we're just going to, okay? So we can, for now, we can use alleles as like a stand-in for gene or for traits, okay? So when we're talking about microevolution, we're talking about seeing a change in traits, in alleles, right, and gene frequencies over time, okay? So that's what microevolution is, all right? So we're going to talk about the different causes of microevolution, okay? Sorry, interruptions. Okay, so where were we? So we have a definition for microevolution, okay? So now what we're going to talk about is we're going to talk about all of the different things that can cause microevolution. So the first one we explained in much detail, right? So one of the potential causes of microevolution is natural selection, okay? And natural selection is the cause of microevolution that is adaptive, right? That allows populations to become more well adapted for their environment, okay? But there are other things that cause microevolution, change in allele frequencies in a population over time. And so let's talk about those, okay? So we're going to do this in a pretty general sense. We're not going to worry about the numbers so much here, or calculate what's P and Q and how are we going to calculate it. And we're not going to do that, okay? But we're going to talk about these concepts, okay? So causes of microevolution. Number one is natural selection. Check, okay? The second one we're going to talk about is genetic drift. Genetic drift is when allele frequencies change, but rather than it being due to natural selection, it's just due to chance, random chance, okay? Genetic drift tends to happen more in smaller populations than in larger populations, okay? But the key here is the randomness of the whole thing, okay? So in this example, we have a population of flowers, right? And so you can see, you don't know what these R's mean yet because we haven't done genetics, but that's okay, okay? But this population of flowers has genes that are responsible for the flowers being red or being white, okay? And so let's say that there's a early, winter storm, right? That randomly, right? So not because anybody is better suited to deal with a storm or not, right? It's completely random. Half the population dies, okay? So then the next generation, you might end up with a different frequency of alleles based on who survived, right? So if it was only the ones that got circled that survived, right, the overall makeup of that population, the makeup of the gene pool, okay, is going to be a little bit different, okay? Now let's say there was an even worse storm, right? So another storm, woo, right? And now there were only 2 survivors out of the 10 in the population. And once again, who survived didn't have anything to do with like being better suited or not. It was completely random. It was just like a big freak incident that just killed a bunch of plants, okay? And only these 2 survived. Well, now, because of the genetic makeup of those 2 individuals, now all of their offspring are these red flowered plants. And essentially that other allele, right, that other gene, the little r that produces the white flowers, disappeared completely, okay? And so we'll talk more about what the letters mean and all of that when we get to genetics. But for now, yeah, just this idea that we had a change in the frequency of what genes are in the population, but that change isn't based on being well adapted. It's based purely on bad luck, essentially. Okay? All right. So there are different examples of genetic drift. One of them is called the bottleneck effect or bottlenecking. For my cheetah lovers, bottlenecking is an interesting phenomenon that actually is likely to have had a really, really big impact on the gene pool of cheetahs. So all of the cheetahs that are alive today, their genetic diversity within their population is incredibly small because at some point in their past, right, the population of cheetahs took a huge hit. So the majority of the population was killed. Once again, it was due to extreme change. It wasn't, you know, some individuals are more well adapted than others. It was pretty random. Okay. But we went from this huge varied population to this really, really, really small population. We call that bottlenecking, right? Because if you imagine that this bottle, you know, kind of represents all the different genes that can exist in the gene pool, right? And so that's our original population. And then you have this event that like kills most of the population. Only a few survive, only a few make it out of the bottle, okay? Then the survivors now are going to be the, you know, source of the gene pool for the next generation. And if only a few survivors make their way out of the bottle, right, then this, you know, population isn't going to look the same as this population, right? So the original population had, looks like probably equal numbers of purple and green. And then it also had these little orangey ones, right? But after the bottlenecking event, you end up with way more purple than green, and orange disappeared completely. Okay. And so we know that cheetahs experienced a bottlenecking event because they are so genetically similar to one another. And that's actually one of the things that's really impacting their, you know, risk of, you know, they're at high risk of going extinct because if a disease comes along that is dangerous for them, because they're also genetically similar, it'll probably wipe out all of them, right? So cheetahs are in a really precarious kind of situation, unfortunately. Okay. So anyway, okay, population bottleneck that happened about 10,000 years ago. So bottlenecking is simply one type of genetic drift. Okay. Another type of genetic drift is the founder effect. So founder effect is pretty interesting. So founder effect, same idea, right? You start off with this large population, and the founder effect, instead of it being, you know, some sort of crisis that makes the population smaller, what happens in the founder effect is you have a large population. Some individuals leave that population to establish a new population, right? So the particular example that I'm giving you here is a human example, but this happens with, you know, all kinds of animals and plants, okay? And so the particular example in this case is polydactyly. So polydactyly is a genetic condition where individuals have more than 5 fingers and toes, okay? Polydactyly in, you know, the general population is actually quite rare. But in certain isolated populations, one specific population that we're going to talk about, it's actually really common. So the Amish are a group of people that live in Pennsylvania and kind of that area. And the reason that they're subject to the founder's effect is that even though they, you know, live within the US, they're a fairly isolated community, right? So they tend not to, you know, interact much with people outside of their small population. They tend to you know, meet and marry people within their community, and in that particular population, polydactyly is way more common than in most human populations. And the reason is that one of the founders, one of the first Amish folks that sort of established this community, right, had polydactyly. And so because that population is based on a very small number of individuals that founded that community, right? We have this much higher proportion of polydactyly than we see in the general public. Okay. Anyway, there's a cool X-ray showing really good polydactyly. Sometimes, right, polydactyly produces a sixth or seventh digit that is functional and useful and normal. Other times it's like a nubbin, right? Polydactyly is also very common in cats, and it can be toes too, not just fingers, but it can be toes. It's very common in cats. And people, I would argue that it's part of the reason it's so common in a lot of house cats is because it's cute. And so, you know, people find it charming. So my two cats, Mario and Luigi, supposedly they're brothers. So when we adopted them from the animal shelter, they said they were litter mates. They were the same age. I don't know that they were actually litter mates. They might have been. It's hard to know. One of them has polydactyly, like hardcore polydactyly. So typically in cats, they have 5 toes on their front feet and 4 toes on their back feet. That's like standard for cats and dogs. Okay. But Luigi has an extra toe on both of his back feet. So he has 5 toes on his hind feet. And on his front paws, he's got his normal 5, plus he's got like a bonus thumb. Plus he's got like a little nubbin in between his 2 thumbs that's like it's got like a nail, and it's a little bit of a toe. It's not like a full toe. So I like to say that he has 6.5 toes on each of his front paws. So Luigi's feet look like catcher's mitts because he's got all this like extra toe business, right? And so when he grabs you, you know it because he's got extra toes. 6 claws. The little halfie doesn't get sharp. It's just this weird little stump. Anyway, and so you may have heard of cats that have extra toes. Ernest Hemingway, the writer, was enamored with polydactyl cats. And so some people call them Hemingway cats because he had like a colony of cats that lived at his house that just, you know, they were all polydactyl, right? And he just loved them. So some people call them Hemingway cats. Anyway. And if you go back and visit his house now, the cats, like future generations of those same cats still live there. So if you ever have the opportunity to visit Hemingway's house, right, there's just this like population of like semi-feral, you know, cats that live in and around the house, and they're all polydactyl, which is kind of entertaining. Anyway. Okay, so that is another example of genetic drift. So the punchline for genetic drift is the gene frequency changes because it's microevolution, but unlike natural selection, it's not necessarily adaptive, and it's due to chance, right? It is completely due to chance, and it tends to be present in small populations more than large populations, okay? And then our 2 examples of genetic drift were bottlenecking and the founder effect. Okay, so all genetic drift, but just like the cause of why the genetic drift happened is different. Okay, another phenomenon that can lead to microevolution is gene flow. Now, superficially, the words genetic drift and gene flow sound very similar. They're not the same though, okay? So what happens in gene flow is about genes flowing in and out of a population due to immigration and emigration. So immigration means you're moving into a population, emigration means you're moving out of a population. And so they, you know, kind of go together, because if you're leaving one population, if you're emigrating from one population, you're immigrating to another population, okay? And so I like to show this picture. This is so old now, this picture, but right, what does it say, 93? That's ridiculous. Anyway, some of you weren't alive then. Okay, so 1993. Probably most of you weren't alive then, which is so disturbing to me. I was a freshman. Anyway, back then, this technology was kind of cool. So what they did is they took a bunch of images, you see all the images in the background of that magazine cover. And what they did is they took a computer and they like fused all the images together to make her. So she's not a real person, right? They just used a bunch of images to sort of create her. And so, you know, looking at the point of this issue of Time was talking about, you know, multiculturalism and, you know, all that kind of stuff, and it, whatever. Okay, so gene flow, the reason I like to show this is that gene flow, if there's a lot of gene flow happening between populations, it tends to reduce differences between populations, right? So for much of human history, people were fairly isolated, right? People lived in a small community, right? You didn't travel much. And if you did travel, you didn't travel very far because it took a long time and it was expensive and right? Nowadays, I mean, COVID aside, people can travel all around the world in, you know, no time at all. So human populations are experiencing quite a bit of gene flow, right? Sort of reduction in differences because human populations aren't as isolated as they once were, right? And so we see a lot of gene flow happening within our own population, but that's true of other organisms as well. If there's a lot of immigration and emigration happening, then what's essentially happening is gene pools are mixing and reshuffling and getting new genes and all of that, okay? Which causes populations to become more similar to one another, okay? So the premise of this is like, eventually we're all gonna look like this lady because she's a little bit of a mixture of everything, okay? I'm just saying. Anyway, all right. So this little infographic kind of explains that. Okay. So gene flow. The last thing. No, it's not the last thing. It's almost the last thing. The last thing that leads to that potential cause for microevolution. So let's recap. Microevolution, change in allele frequencies, change in gene frequencies in a population, can happen due to natural selection. It can happen due to genetic drift, right? And there were a few examples of that. It can happen due to gene flow. And another potential cause is mutations, okay? Mutations also are the only way that you get completely new, unique traits. So we talked in one of the other videos about how natural selection edits, but it doesn't create new traits, right? So it creates changes in, you know, how abundant certain traits are, but the only way to get completely new traits is through mutation. And so we're not going to talk about mutation for a little while. This is a little bit down the road, okay? But we will get there, okay? So mutation is essentially what a mutation is a change to DNA, which, you know, ends up with a change in a gene, which ends up with in a change in the way that a particular trait is expressed, okay? So more about mutations later, but that's our fourth potential cause of microevolution. Okay, the last thing we're going to talk about here is we're going to talk about a concept called sexual selection. Sexual selection is the confusing sibling of natural selection, okay? And there's different types of sexual selection, so I'm going to give you a couple of examples. All right, let's say here that it's our guppies again, right? So we're doing another guppy experiment, right? What's different this time? So we still have our diverse population of guppies that's been split into two tanks. One tank has sandy gravel, the other one has coarse, like pebbly gravel. The only difference here is we don't have a predator, okay? Let's see what happens. Let the guppies be guppies. They're like rabbits of the water, man. They just make babies like crazy. Guppies are, if you have a tank with guppies in it, you will constantly be like, somebody take some guppies, somebody take guppies. They are incredibly productive. Anyway, okay. So 15 generations later, what happens? All right, well, so this tank, 15 generations later, we end up with a population where the guppies are kind of blotchy. And then in this tank, 15 generations later, we end up with guppies that are speckly. Oh, I went too far. Hold on. Guppies. Where are my guppies at? I got excited with the scrolling. There, oh no, there we go. Whew. Okay, that's the opposite of what happened before, right? So in this experiment, the guppies in the tank with the chunky gravel got blotchy, and the guppies in the tank with the sandy gravel got speckly. Why is this different? What? Why is it different? You tell me. I'm gonna have a sip of coffee. So, first of all, what's different about the tank? Well, there's no predator this time. Okay, so nobody gets eaten. All right. So why wouldn't the population just stay the same? Why would it? I mean, it changed. It just changed in the opposite direction. So why would that happen? All right. So think about mating. Right. One of the things about reproduction, sexual reproduction specifically, is you have to be able to find a mate, right? And it's a lot easier if they stand out, right? So in the case of guppies, right, who is it easier to see? They're not particularly picky, guppies. They're not very smart. So they're not particularly like picky about who they mate with, but they're more likely to mate with somebody that they can see easily. Yeah. And so if you live in a tank with this kind of speckly, sandy bottom, and you're a speckly looking guppy, you're not going to get as much action, right? As if you're a blobby guppy, right? Because the blobby ones are more visible. Okay. So over time, the population became more and more sort of blotchy because that stands out against that background. Yeah. And then the opposite happened in the other tank. So, right, if you're blobby and blotchy, you're going to blend in more of the background. It's going to be harder for potential mates to find you. Right? So being speckly is an advantage in this tank. So this goes back to this idea that natural selection, there is no one like goal. It depends on the circumstances. And since there's no predator in this case, right, what's driving natural selection is actually sex, which is why we call it sexual selection. So it's mating, right? Sexual selection does weird things. Okay, so let's talk about peacocks because they are like the quintessential example of sexual selection. All right, so let's look at this bird. He is beautiful and radiant and splendid. Look at him with his super shiny blue feathers on his chest. They reflect light. He sparkles from a distance, right? And he's got this ginormous tail with ridiculously long feathers. In fact, so here he is displaying, but even there he's displaying, right? There's the female, by the way, right? Female's all like plain and gray, and the male's like, hey, girl, with his giant tail. So even when he's not displaying, look how long his tail is down here, right? So even when he's not showing off that tail, it is so long, okay? Does that make sense through the lens of natural selection? Okay, so peacocks, peafowl, as they're called in the general sense, males versus females, right? Together, peafowl. Peafowl are basically like overgrown chickens, right? They're prey, yeah. So larger animals want to eat them because I imagine they're delicious. Okay, so if a male peacock, right, if a male has this huge tail and super like shiny, does that help him hide from predators? Absolutely not. There is nothing about him that is going to help him in an interaction with a predator, right? It's going to be easier for a predator to find him. It's going to be easier for a predator to catch him because he's got that big long tail hanging off his butt, right? Like every single outward characteristic of this bird seems to go against the idea of natural selection. Whereas in the female, look at her. So she's gray, she's subtle, blends in. She's got a tail, but it's not like that, right? So it's going to be a lot easier for her to like lay low, right? And avoid being eaten by a predator. So why would this happen? Why would this happen? Why? It sounds like it's counter to natural selection, when in reality, it's not really, it is sort of counter to natural selection if you look at it in a very superficial sense. But if you think about the dynamics of behavior, then it starts to make sense, okay? So there's our beautiful, beautiful male peacock. If you've never interacted with peafowl, by the way, they are very interesting birds. So Descanso Gardens, one of the great botanic gardens in LA, has a population of peafowl that just, you know, they're essentially wild. They run all over the place. There's a bunch of peafowl that live free essentially at the San Diego Zoo. Right, so they're all over the place, and people who live in neighborhoods where they have them hate them because they apparently generate a tremendous amount of poop and they're loud, right? So the males make this, you know, obnoxious mating call sound, and they're just ridiculous. Anyway, so people who live near them hate them, but they're really, really interesting, right? To sort of watch them interact. And so the females are kind of timid and they blend in. The males are like, hey girl, with their like big old tail. All right, so why is that like that? Well, who's he? Why does he have these characteristics? Why does he have these traits? All right, well, he's displaying for the female. And the reason he's displaying for the female is that in this species, and this is true in lots of birds, right? The way that the males attract a female is by being beautiful, right? So a peahen is more likely to mate with a beautiful, gaudy, shiny, huge-tailed male than a male that looks more like her. Okay, why is that? So we see this, we'll get to the why is that in a second. We see this in a lot of different ways. So many bird species have sexual dimorphism, and almost always, so sexual dimorphism means that dimorphism, di means two, morph means form. So the idea of sexual dimorphism is that males and females, the two sexes, appear very different, like strikingly different from one another. It's not true in all birds, but it's true in many birds. And of the two, almost all the time, the males are the ones that are brightly colored or flashy or pretty, and the females tend to be more drab and more hidden and whatever, okay? We also see sexual selection in animals. In a lot of mammals, we see it with like antlers and horns and stuff like that. So these males are competing for mates, right? And so the bigger your horns and antlers are, right, the tougher you're going to be, and you're more able to fight with the other males so that you can control the pack of females, right? So that's another type of sexual dimorphism that we not always, but often see in certain mammals, okay? So generally males have bigger horns or antlers than females typically. If sometimes females don't have them at all. It depends on who you're talking about, but okay. But there are disadvantages to being showy, okay? So I always like to think about elk or deer, okay? So elk and other deer often, not always, but they often live in forests. And the males tend to have these big racks of antlers. Well, if you're living in a forest, how convenient is it to have these big like things hanging off your head? Can you imagine how difficult it must be to like get through the forest with your antlers getting caught on everything all the time? Like, hello, huge disadvantage. Okay, and yet that persists, right? The same way that, you know, being big and fancy, huge disadvantage, right, when it comes to predators, and yet that still exists. Why? Right, well, here's the why. So funny cartoon on the side. that's a joke. Okay, the part you want to look at is you want to look at this. Okay, so This is why sexual selection exists. This is why males often have traits that don't seem particularly adaptive. They don't seem particularly useful, right? And in fact, sometimes seem harmful, right? This is why these things exist. Okay, so a fact about males and females throughout all organisms, whether we're talking about plants, whether we're talking about animals, whatever. Females, the gametes, gamete is a general term for eggs and sperm. Females make eggs. Eggs are larger and they take more energy to make. And so females make fewer eggs than males make sperm. Okay. And that's sort of the defining characteristic biologically of maleness versus femaleness is, do you make eggs or do you make sperm? Okay. Not the same as gender. Okay. But right. Anyway. Okay. So as a general rule, because females make fewer, more energetically expensive gametes than males make, females are often, particularly in animals where behavior is important, like birds, like many mammals, right? Kind of the smarter animals. Behavior is really, really important, okay? And the females will often choose males based on, you know, making a good investment, right? If you're gonna, you know, mate with him, you only make so many eggs. If you're gonna mate with him, you better pick the best possible male you can, right? Okay. Whereas males are like, I don't care, I make so many sperm, I'll mate with anybody, it's fine, whatever, no worries. Okay, so males typically are not very choosy, right, in the animal kingdom, right? Whereas females often are. Okay. So in this little graphic, what we're looking at here is they're saying, okay, so let's say we have males that have short tails versus males that have long tails. Remember those long tails, not only does it take more energy to make a long tail than a short tail, right? So it's costlier as opposed to cheap. But the other thing is that long tail means that you're much more likely to get eaten by a predator and, you know, struggle, okay? All right, so right? So that's sort of the one side of the table. The other side of the table says sort of genetic qualities, right? So how tough are you, right? What does your ability to survive look like? Okay. So from a female's perspective, if she is interacting with a male that has a short tail, regardless of his genetic quality, if he's otherwise tough, right? If his fitness is otherwise, you know, likely to be high or not, right? It doesn't really matter because he's got a short tail. He's not, right? He's not going to be subject to, you know, extreme predation as much as somebody with a long tail. Okay. Whereas if a female is looking at a bird with a long tail and he makes it to adulthood, he makes it to sexual maturity, right? Just the fact that he has that impediment, right, that big, long, ridiculous tail, means that he must be pretty tough. He must be smarter or faster or stronger or whatever, right? Have characteristics that help him avoid being prey to a predator that you can't see in the short-tailed bird, right? So the short-tailed male, he might have great genes, but the female can't tell just by looking at him. Whereas the female can tell, oh, he's got a big long tail. Therefore, if he's still alive with that impediment, right, he must be real good genetic quality, because if he wasn't, he would be dead, right? So that's sexual selection. And so sexual selection is kind of like a weird alternate form of natural selection where you end up with traits becoming common that don't seem very adaptive on their face, right? So they don't seem like things that are beneficial. They are, but it doesn't seem like it. Yeah? Anyway, so that's sexual selection. One last thing, and I'm not going to talk about this because you can read about this and it's in your homework, is the relationship between malaria and sickle cell. So I'm just going to throw this out here as something for you to kind of do on your own. If you have questions, ask, okay? But but I'm going to throw this out there, something for you to kind of read about on your own. So like I said, in your book, they talk about, I'm pretty sure it's in your book, but it's also in the mastering homework where they, kind of have you think about this a little bit. Okay. Yeah. So that's it for microevolution. So next week, we'll be moving on to macroevolution, which is, kind of similar, but it's a different scale. Okay. All right. If you have questions, ask. You know where to find me. Zoom. Okay? Have a good one.